Hello, everyone. Welcome back, Organickers. We are going to talk about how to name alkanes and cycloalkanes, which is also an important part of this chapter 3 in the textbook. Naming is a really important aspect of organic chemistry. There's so many different complicated structures that if you don't know how to name things correctly, it gets really confusing really fast. So we have a systematic way called by the International Union of Pure and Applied Chemistry. So it's IUPAC, systematic naming for organic compounds that we use, which helps clarify one structure from another. So we're going to learn how to name alkanes and cycloalkanes, and then how to extend that also to some of those functional groups that we were talking about back in chapter 1. So pay attention. The last lecture was about constitutional isomerism, and one easy way to tell if something is the same compound or is a constitutional isomer is actually to use the IUPAC system and name the two different structures that you're looking at. If the names are identical, they're going to be the identical compound. If their names are different, they're going to be constitutional isomers. So sometimes you don't have models to build and to try to assess if a structure is something that's the same or something different when it's drawn differently. So you can use your naming skills in order to figure out if it's the same or if it's a constitutional isomer. So let's start talking about how to name alkanes, cycloalkanes, and then extend that system to a couple of the common functional groups. Okay. Many organic compounds have common names. For example, this is called formic acid, but it's actually methanoic acid, according to the IUPAC name. This is called urea. This guy is morphine. Now, obviously, if you tried to name this very complicated structure using IUPAC, you get probably a page worth of compounds because it's so complicated. This is actually called barbituric acid, and this is named because the guy who actually discovered this named it in honor of some woman that he knew named Barbara. So think about this. This was isolated from urine, it's urea. This is isolated from ants. It's named for the Latin word ant, which is formica. This guy over here is named after some woman named Barbara. So the common names are kind of all over the place. What we need is a systematic name that allows us to name things that we've never seen before in a routine way so other people can understand the structure and be able to draw the structure based on a systematic name. So in organic, we use this IUPAC system. Again, this is from the International Union of Pure and Applied Chemistry, and it outlines very, very thorough rules which allow the systematic naming of organic compounds. There's usually different components to the IUPAC name. I want to look at the parent name, which is always related to the longest continuously connected carbon chain. I want to name substituents. Those might be various branches that occur off of my longest carbon chain. And an important piece is I want to be able to describe the location of those substituents. We saw before in our constitutional isomerism discussion that if I had something that was connected to the 2 carbon or something that was connected to the 3 carbon, right? this is a 1-carbon branch called a methyl group, but I have to be able to distinguish where it's located. Is it on the 2 or is it on the 3 carbon of my longest chain? So the location of substituents is going to be extremely important in writing out the systematic IUPAC name. So let's go over the rules. The first thing I want to do is identify the parent chain. This is the longest consecutive chain of carbons. This takes practice. A lot of times you have to go through and count different ways. So I could go through and I could say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 carbons, right? I could also go through 1, 2, 3, 4, 5, 6, 7, 8. Well, that's not as long, so it probably doesn't matter. I could always go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. Well, that's 8 carbons, that's not 9 carbon. And you see what I'm doing? I'm going through various orders of trying to figure out the connectivity in order to figure out what is my longest consecutive chain of carbons. As it turns out, it's the one that I did first. So my parent compound has 9 carbon atoms. That 9 carbon atoms then, according to my naming system, would be a no name. But I do have branches to that, so I have other pieces of this name that would have to be incorporated as well. But for now, you have to be able to recognize the longest continuously connected consecutive chain of carbons. That is what the name of an alkane is based on. If there is more than one possible carbon chain, choose the one with the more substituents attached. Here I have 1, 2, 3, 4, 5, 6, 7, and I have 3 substituents. Here I have 1, 2, 3, 4, 5, 6, 7, but I only have 2 substituents. This is the correct name. This is the correct base name, which would be 1, 2, 3, 4, 5, 6, 7. This would be a heptane derivative. And having the 3 substituents makes this a more correct choice than the other one. My parent names are going to be just like those straight chain names. If I look at the number of carbon atoms, and then I look at the prefix, and then this is the name that I'm going to use as my base name. So if something has 6 carbons, it's going to be a hexane derivative. If my longest chain is 8 carbons, it's going to be an octane derivative. If my longest chain has 12 carbons, it's going to be a dodecane derivative. All of my substituents could increase the carbon content, right? And I'm going to address that when I name substituents that are attached to my longest continuous carbon chain. But the base name is always derived from the longest consecutive carbon chain in my structure. So these are all going to be the base names or the parent names from when I'm naming my alkane. If the parent chain forms a cyclic structure, I'm going to add the prefix cyclo. This is 3 carbons, but it's connected in a cyclic structure. So it's cyclopropane. 1, 2, 3, 4 carbons gives me a butane, but it's cyclo because it's cyclized. 1, 2, 3, 4, 5 will give me the pent for pentane, but it's cyclo. These are called cycloalkanes, and that's the second part of this third chapter, looking at alkanes, which are open chain structures, and then cycloalkanes, which are cyclized structures. So let's think about how I would identify and name the parent in each of the following compounds. Again, sometimes I have to count a couple of different ways. I could have 1, 2, 3, 4, 5. I could have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So my yellow is going to have 6 carbons. So this is going to be a hexane derivative. So my parent name is going to be something hexane. Let's look here. I could do 1, 2, 3, 4, 5, 6, 7. I could also do 1, 2, 3, 4, 5, 6, 7. I have a tie here. I have 7 and 7, right? Let's look at which one has the most substituents. The orange one, the orange has 2 substituents, whereas the yellow has 1, 2, 3 substituents. So I would choose the yellow as the base name. So that would be 1, 2, 3, 4, 5, 6, 7. That would be a heptane derivative. On this compound, I want to look at the longest connected chain. It's going to be the cycle, right? I go here and I stop. These guys are going to be substituents. Just because this is connected, I'm looking at the largest cyclic structure that's connected. So this is 1, 2, 3, 4, 5, 6, 7. This is going to be a cycloheptane derivative that has 2 1-carbon branches. Okay. Once I identify the longest continuously connected carbon chain, which is my parent name, I'm going to identify and name the substituents. Generally, these are going to be alkyl groups. They're branches that also have carbon hydrogen. If I have a 1-carbon branch, again, I use the same prefixes. It's going to be methyl. 2-carbon branch, it's going to be ethyl. So if I look here, I have my 2 carbons, which will be an ethyl. I'm going to use, when my alkyl chain is a substituent on a longer carbon chain, I use this suffix YL. Here I have 1, 2, 3, so that's a propyl group. I have a 1-carbon, that's a methyl group. So this is my ethyl, this is a methyl, this is a propyl. Those are the substituents that I would add to my longest chain, which is this guy. And it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is going to be a decane derivative. And I'm going to have to name and locate each one of these 3 substituents to get the valid name. Here, my ring can either be the parent chain or a substituent. This is a 6-carbon ring. This is a 3-carbon piece. I'm going to name the parent as the ring because it has more carbons. So this is going to be a cyclohexane. Notice in this example, I have a 3-carbon chain and I have a 4 carbon, or if I have a 3 carbon ring and I have a 4 carbon chain. So I'm going to name it based on the larger amount of carbons, which means this ring, which is cyclopropane, goes to cyclopropyl. It's on the first carbon of my 4 carbon chain, so I have to give the location as 1 dash. So if my ring is larger than the attachment, name it according to the ring. If the number of carbons in the ring is less than the chain, name it the ring as a substituent. What if I have something that actually has a complex branch? So here's my longest chain, and this whole thing is my branch. Well, I have sort of an alkane attached to an alkane. So I have 1, 2, 3, 4. And then on my second carbon, I have this methyl group. This 4 carbon is a butyl group. Overall, it's got 5 carbons, but I want to name it sort of systematically. So I'm going to number the longest carbon chain within the substituent. And I always start with the carbon that's attached to the parent chain. That's number 1. I name the substituent, which is butyl, right? That's the longest chain. Then I'm going to name and number the substituents' side groups. So on my second carbon of my butyl group, I have a methyl. And then I'm going to put this whole thing in parentheses and just sort of attach it at the beginning. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it could be on the 6th carbon, or I could name it this way: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It doesn't matter. The number of this carbon that bears the substituent doesn't matter. What I know is it's in undecane because it's got 11 carbons. So I would write this as 6-2-methyl butyl, because that's the substituent, undecane. This just tells me the substituent is located on the 6th carbon. Now, some of the substituents have common names, especially if I only have 1, 2, 3, or 4 types, carbons in the chain. So there are 2 different types of propyl groups based on branching. I have this straight chain, or I have this branched, right? This is attached at the first carbon of the propyl group. This is attached at the second carbon of the propyl group, or I could call it 1-methyl ethyl. This is more commonly used. This is going to be isopropyl. So it kind of looks like a whale tail to me. And when I have my whale tail, I use iso. And you're going to see I can have isobutyl and isopentyl as well. When I have butane, there's actually 3 different types of butyl. There's this continuously connected 1, 2, 3, 4 straight chain. Here, I'm connected on the second carbon of the butyl. Here I'm connected at the first carbon. Or I could have a branch on my butyl and still be connected here. Notice isobutyl, my whale tail. When I talk about iso, I'm connected to the first carbon, but I make that whale tail. This is another example. I have my carbon, and then I have basically 3 carbons that branch, which is called terp. This guy is attached to carbon number 2, which is a secondary carbon, which we'll talk about later. But when it's attached to carbon number 2, it's going to be sec-butyl. So I have the straight chain butyl, the straight chain attached to the second carbon of the straight chain, which is sec-butyl, or I could call it 1-methyl-propyl, but this I'm not going to use so much in this class. If I had regular organic 1 or 2, I would use that more often. This with my whale tail, right, 1, 2, 3, 4, I still have 4 carbons, so it's a butyl attachment. It's just branched, so it's called isobutyl. I make that whale tail. And then when I have this tertiary carbon, which is the carbon attached to 3 other groups, I'm going to call this terp-butyl. You need to know these structures because these are going to be commonly used in many, many, many different situations. And you're going to use them when you do these names. These are critical pieces in our naming strategy. So again, this is what you need to know. Methyl ethyl, when I have propyl, I could have propyl and isopropyl. When I have butyl, I could have straight chain butyl, isobutyl, which makes my whale tail, sec-butyl, or terp-butyl. So when I have 3 carbons, I have 2 choices. When I have 4 carbons, I have 4 choices. And these are the ones that you have to be very, very concerned with. We're going to use these all the time. Propyl isopropyl, and then butyl, and then these other guys. You need to know these. You need to be able to recognize them. You need to be able to name them when they're attached to longer alkanes. This is a really important chart. And remember, the tert is for tertiary, because the attachment is on a tertiary carbon. And then the sec is for secondary, because the attachment is on a secondary carbon. We're going to explain that a little bit later. So to put the whole name together, I am going to number the longest carbon chain. So if I look at these two, I have my methyl group on carbon number 2. So I do 2-methyl. On this, these are isomers, right? These are constitutional isomers. And you can tell that because here on the 3rd carbon, I have that methyl group. So this compound is 2-methylpentane. This compound is 3-methylpentane. Just by naming them, notice I can tell that they're constitutional isomers because they have the same number of carbons total. They have the same formula, which is going to be C6H14, but they do have different connectivities. How do I number? Sometimes there's 2 different ways to number. Do I go left to right? Or do I go right to left? Well, the answer is if I have 1 substituent present, I'm going to number the parent chain so that substituent has the lowest number. Here, it would be number 2. Here, it would be number 6. This is not correct. This would be 2-methylheptane. I would not call it 6-methylheptane. When multiple substituents are present, I'm going to number in the direction that gives the first substituent encounters the lowest possible number. So here I go 1, 2. I encounter my first substituent as 2. Then my next substituent is on carbon 5. My next substituent is carbon 5. If I number from this direction, I don't encounter a substituent until carbon number 3. So this is the correct direction of numbering. If there is a tie, I'm going to number the parent chain so that the second location gets the lowest number possible. So I have 2 and 2. I encounter my first substituent on carbon number 2, regardless of if I go left to right or right to left. My second substituent, though, is on the 3rd carbon in this structure. My second substituent isn't until the 5th carbon on that structure. So this is the correct structure. My numbering would be 2, 3, 6 for my substituents. If there is no other tiebreaker and I have a tie, I'm going to assign the lowest number alphabetically. So if I put bromo, which has a B, as carbon number 1, that's going to be chloro, which has a C, as carbon number 1. So this would be the correct numbering. The same rules apply for cycloalkanes. Here, I start out with a substituent. I go 1, 2, 3. So I have 2 substituents because both of these are methyl groups. So my substituents would be on carbon 1, carbon 1, carbon 3. If I start numbering here, my substituents would be on carbon 1, carbon 3, carbon 3. Right, here's 1 substituent, 2 substituent, 3 substituent. This is the lower best numbering system for this cyclic structure. So once I identify all the pieces, I've got the numbering down, I know the name of the substituents, I know all of these different things. I'm going to put the number and the name of each substituent before the parent chain in alphabetical order. Now, if I have 2 methyls, I'm going to say dimethyl instead of like 3-methyl, 4-methyl, right? If I had like this, I would have 1, 2, 3, 4. I'm not going to say 2-methyl, 3-methyl butane, right? I'm going to say 2, 3 dash dimethyl butane. That's when I have multiple of the same substituent. I'm going to use di, tri, tetra. Notice even though they're the same substituent, each one is on a different location. If I had this, this would still be 2, 2 dash dimethyl butane. I still need 2 locations, even those locations are the same, right? The important part is any di or tri or sec or tert is ignored when alphabetizing. Iso is counted. So isobutyl starts with an I and not with a B. So here's my summary. Identify the longest continuously connected parent chain of carbons. Identify and name the substituents. I'm going to number the parent chain and assign a location to each substituent, and then I'm going to list the numbered substituents before the parent name in alphabetical order. So here's an example, and this happens to be cyclic. I'm going to count in this direction to give the lowest number of substituents. On my 1 carbon, I have a tert-butyl group. On my 2 carbon, I have an ethyl group. I have methyl on my 4 carbon and a methyl on my 4 carbon. But what I'm going to call that is 4,4-dimethyl. Tert isn't in the alphabetical, so I have B, I have E, and I have M. Di is not in the alphabetical either. So I have 1 tert butyl dash 2 dash ethyl dash 4 comma 4 dash dimethyl cyclohexane. So this is how I name the entire compound. All right, let's look at this one. Find the longest chain as the parent. Do I want to go from this direction, or do I want to go, do I want a number from left or from right? That's my longest carbon chain. So if I number, I could number it 1, 2, 3, 4, 5, 6, 7. Or if I number the other direction, I'm going to have 1, 2, 3, 4, 5, 6, 7. Notice which one I choose. If I use this one, my substituents are on 4 and 5. If I use this numbering, my substituents are on 3 and 4. So I'm going to use this numbering because that gives me the lower number. Now, what are my substituents? I'm going to have a 1 carbon branch here and a 1 carbon branch there. So I have 2 methyl groups. So that's going to be dimethyl. I still have to put the locations of those 2 groups though. So what I'm going to do for my complete name is I have 3, 4 dash dimethyl heptane. I don't need those parentheses. I don't know why they're there. This is the name as I would put on my paper. Here's another example. This one, right? Figure out the longest continuous carbon chain, and you might have to go in a couple different directions. You might think 1, 2, 3, 4, 5, 6, 7, 8, 9. You might think 1, 2, 3, 4, 5, 6, 7, 8. You might go in these different directions, right? But what you want to come back to is always pick the longest carbon chain. So for example, I could have a 6 carbon chain, an 8 carbon chain, an 8 carbon chain. Well, these are tied. So which one do I pick? Here I have 1, 2, 3 substituents. Here I have 1, 2, 3 substituents. So what do I do? Well, that's not the longest carbon chain, because if I look at this one, that's my longest carbon chain, which is a 9 carbon, so I know no name is my parent. Then I'm going to number, right? If I go from this direction, I get substituents on the 3, 4, and 7 carbon. If I go in this direction, I get substituents on the 3, 6, and 7 carbon. This is my lower grouping, so I'm going to use this numbering system instead. So what do I have? On my 3rd carbon, I have a methyl. On my 4th carbon, I have an ethyl. And on my 7th carbon, I have a methyl. So I have ethyl, and then I have a 3,7-dimethyl. E comes before M. I ignore the di. So the name is 4-ethyl-3,7-dimethylmonane. And this is the final answer. One more example. Let's look at this guy. All right, sometimes you got to count and figure out what is the longest chain, and you have to count from multiple directions. Well, I have 4 different ways I can count. Maybe more, but this is what I'm putting down. My longest carbon chain is going to be this one, which happens to have 9 carbons. So that means no name is going to be my parent. Now, do I number it 4, 5, or do I number it 5, 6? I'm going to use the 4, 5 because that gives me the lower numbering for my substituents. Now, what are my substituents? This is my whale tail, right? And I have 1, 2, 3 carbons. So this is isopropyl. This also has 1, 2, 3, 4 carbons. So it's a butyl. But because I've got this 3 carbons attached to that 1 carbon attached to the chain, this is going to be a tert butyl. So my full name would have a 4 isopropyl and a 5 tert butyl. So the complete name is going to be, remember, B comes before I, and yes, I is used in the alphabetizing system. Remember, ISO is not excluded unlike some of these others. And what I'm going to have is 5-tert-butyl-4-isopropyl, no name. Okay, I think we're going to cut it here. And then when we come back, we'll do one more lecture that looks at cycloalkanes, how do I name them, and then other substituents, because this has gone long enough. So here we go. I will see you in a bit. Bye-bye.